discussion on khovanov-homology.
Thank you. So I left us yesterday in a sort of awkward spot where I'd given you this big and complicated definition of this tensor category that I'd called C star. And I'd said that, that we'd crept up on the definition of khovanov-homology. The idea is just that the invariant of some link is, well, you think of that link as giving you an element of some home space in this category C star, and it's just home from 0 points to 0 points. This is just sort of thinking that a link is a special case of a tangle with no points at the top and bottom. But let's just make this much more explicit right at the beginning now, just for the sake of everyone having a clear recipe for putting this together. And I'll do an example at the same time. Okay, so here's the rule. Let's make a big cube. People who've seen khovanov-homology before yesterday will be familiar with this starting point. The vertices are just, well, I'll say complete resolutions of L. So that is, you take each crossing and you turn it either into the 0 resolution or the 1 resolution. So the vertices of this cube are just systems of closed circles. And I guess I'll tell you here a grading and a homological height to attach to each vertex with a factor of q to, well, I'll get this number right just so you have the recipe, but it's a little bit ridiculous. So with the coefficient of q to the, let's see, so it's the number, I'll write this. This means the number of positive crossings for which we've used the 0 resolution, okay? Plus twice the number of positive crossings for which we've used the 1 resolution, minus the number of negative crossings for which we've used the 0 resolution, minus 2 times the number of negative crossings for which we've used the 1 resolution. Okay, so now each vertex of the cube is a complete resolution of the link and some factor of q sitting out the front. And homological height the number of positive crossings which we've given the 1 resolution minus the number of negative crossings which we've given the 1 resolution. Okay, and now let me tell you the edges of this cube. So the edges are just saddle cobordisms changing a single crossing. And these are directed edges. So they go from the 0 resolution to the 1 resolution for positive crossings of the knot, and from 1 resolutions to 0 resolutions for negative crossings of the knot. And if you stop and check, this rule about which direction the edges point is consistent with this height function that I've put on the vertices of the cube. The edges always connect a vertex at 1 height with a vertex at the height 1 greater. And let's attach on the, well, put with these saddle cobordisms a sign -1 to the number of 1 resolutions for later crossings. So let me explain later. For this rule for the signs to make sense, I have to get you to pick an ordering on all of the crossings appearing in the diagram of the knot. And if you pick different orderings, you'll build slightly different cubes with signs in different places, but the answer won't matter in the end. Okay, and the point is that this is a chain complex in this crazy category Hom C without the star, 0 to 0. I mean, the point is that complexes in Hom C without the star are elements of Hom C with a star. That was the idea yesterday. Okay, and so this more explicit version is the definition that you see, for example, in, I'll just write up the archive reference in case people would like to see that. This explicit version written out in more detail, and that'll help you unravel all of the nonsense that I said yesterday about graded tensor categories. Okay, so let me do an example as well, just illustrating this. Okay, so the khovanov-homology of, oops, that's not the nut I wanted to draw. Of the Hopflink, which I'll draw like this. Well, it's got two crossings in here, so it's just going to be a two-dimensional cube. And if you follow all of the rules in the recipe here, you get this gadget. There's no need to copy down this diagram. If you picked up a copy of the notes yesterday, or replace the 2 in this URL with a 1, you'll get exactly the copy of the diagram that I'm copying at the moment. Sorry, I need to add a q to the 4 there. And, oh, what else do I need to put? I'll draw an underline here. Remember the underline was notation I had yesterday telling you that this is the object in homological height 0. So this is height 0, this is height 1, this is height 2. These arrows, which I haven't labeled yet, are the differentials. And I'll just draw the differentials like this. It's just a notation to tell you where to do a saddle cobordism. So here you get from this diagram to this diagram by doing a little saddle in this region here. Okay, so that's all very well, but the invariant that we have at the moment for a knot is a pretty awful thing. Who wants some complex in some pretty abstract category as the invariant of a knot? What we want now is a standard form for elements of this Hom space where the invariants of links live. So just like for Templey-Lieb, we had that Hom in Templey-Lieb from 0 points to 0 points was actually just isomorphic to Laurent polynomials in Q. We want something like that. And the theorem here, I think I'm intending to prove the theorem right now. Yep, okay. So the theorem right now is that crazy complexes in this category, well, this Hom space, remember that's just a category, is isomorphic to the category of bigraded vector spaces. And I'm going to describe this isomorphism 2 times. The first time, I'll describe it in a way that feels familiar if you already like khovanov-homology. And in particular, it's the one and only time in these 2 lectures that I'll use the word homology, not as part of the phrase khovanov-homology. And then the second time, I'll describe the isomorphism slightly differently and actually convince you that this is an isomorphism and all these complexes really are, well, yeah, that we really get this. Okay, so first, let's try this. So we have a functor. Let's see. Let me say, first of all, this one. Yeah. No, it doesn't mean that. Remember that you can take any link and stick it into this Hom space as a complex. But I'm certainly not saying that that's surjective. So really there's two compositions here. Yeah. Sorry, two maps. You can take links and put them in here, and then turn anything in here into a bigraded vector space. But yeah, I wasn't saying that. Okay. So what's this functor? Well, if I'll tell you where it's to and from, that'll make it much easier. So if I have an element of this category, of this Hom space, this is C without a star. So the Hom space here consists of temporally Lieb diagrams, maybe with factors of Q, maybe with direct sums. No complexes here. Two vector spaces. What's this functor? Well, it just looks at all of the surfaces, modulo all the relations that we described yesterday, from the empty diagram to whatever diagram you're thinking about. Okay? And let's, first of all, beef this functor up a little bit and take the direct sum over all integers. I guess S is safe. We'll take the Hom from Q to the S times the empty diagram. And now this is a functor to graded vector spaces. And the grading is just given by that direct sum. The reason why we want to do this is, remember, in this Hom space, the Hom space that describes the surfaces we care about from one diagram to another, there's this condition on the Euler characteristic. And taking this direct sum just allows all Euler characteristics. Okay. So we've got that guy. Well, we can apply this functor to a complex here. So remember, the elements of this Hom space here are complexes in this category. So each chain group is an object in this category. Each differential in a complex here is a morphism in this category. So we can just apply this functor sort of term by term along the chain complex. So given a complex X, in the homotopy category, we can apply this functor get a complex of graded vector spaces and then take homology. Okay. And that gives us a bigraded vector space. There's the internal grading that came from looking at the different Euler characteristics of surfaces here, and then there's the homological grading after we took homology. Okay, so that certainly took us from here to here. But the worry, I guess I want to use this board, the worry is that we might have lost a whole lot of information. In particular, when we took homology, who knows what we're throwing out of the homotopy type of that complex that we started with. And so the second version of thinking about the map in this theorem is just going to be, well, you don't need to worry about that. Actually, in some sense, all of these complexes are homotopy equivalent to their homology. So let's think about that. So what are the objects in just Hom C, not Hom C star? Well, these are just temporally Lieb diagrams, but with no boundary point. So they're just some collection of circles. And we know that a circle is isomorphic to direct sums of copies of the empty diagram. So objects in here are all isomorphic to direct sums of, well, Q to the S times the empty diagram for different values of S with whatever multiplicities you like. Okay, so every complex in Hom C star, 0 to 0, has a representative where all of the chain groups are of this form. So let me just schematically indicate something there, yeah, let me actually do it in this example. Okay, let's just use the isomorphism to remove all of the circles in this diagram. That complex up there is isomorphic to one that looks like this. Each circle, remember, turns into a Q times the empty diagram, direct sum Q inverse times the empty diagram. So I'm just taking Q squared times Q plus Q inverse squared. Okay. And over here, we'll get and over here, we'll get oh, did I? Sorry. Yeah, there were two copies of this guy. Yeah. I'll write 2 instead of writing direct sums. Yeah. Okay. So what are the differentials now here? Well, this differential here has to be some little matrix whose matrix entries are maps from one direct sum n to another. So it's a little 4x4 matrix. But what are the matrix entries? Well, this is in the filled-in circle direction, the surface direction. From the empty diagram to the empty diagram. And even if we put factors of Q in, so let's look at Q to the S times the empty diagram, Q to the R times the empty diagram. Well, this is just C generated by the empty surface if S equals R and 0 otherwise. There are no possible surfaces with Euler characteristic 0. What did I want to say? Well, all of the surfaces, the closed surfaces, that don't have Euler characteristic 0 are equal to 0 because of our relations. For example, you might think that this guy here should be a cobordism from the empty diagram to the empty diagram, and it would be this would look like it's a valid map from Q to the S times the empty diagram to Q to the S plus 2 times the empty diagram if you go look up the rule about Euler characteristics. But this is equal to 0. I guess a good exercise is to see this follows from the relations that we talked about earlier. And you can check, in fact, that everything that doesn't have Euler characteristic 0 is actually equal to 0, and everything that has Euler characteristic equal to 0, that is disjoint unions of tori, are actually just multiples of the empty diagram. So that's the only Hom. So what's that saying? Well, just all of these matrix entries here are either 0 or a complex multiple of the empty cobordism. Okay. So what's the point of that? Well, every matrix entry in the complex, I guess I'll move over here. Every matrix entry in the complex is either 0 or invertible. And this is the first point, I guess, where it matters that I wanted to work over C, or at least a field. It occurs to me that I should say a little bit more about why this was true. So let me go back to that example that I had before. Let me just recall some of the relations. The important one that we're going to use is that any time you see a tube in one of these surfaces, this is just equal to a sum, a linear combination of two surfaces. You place the tube with two disks and put a dot on one of the two disks. So an immediate consequence of this is that if you have a little bit of genus anywhere, this is just equal to 2 times that sheet with a dot on it instead of the genus. You just apply this neck cutting relation across here and see that both of these terms collapse because the dots can both move to the sheet. Okay, in particular, that, for example, means that if you have a torus that's equal to 2 times a sphere with a dot on it, which was equal to 2, because one of our relations was that a sphere with a dot on it was equal to 1. And let me just do another sort of example calculation that lets you check this. I said a moment ago that because of the relations, this guy has to be equal to 0. Well, why is that? Well, okay, let's just use this backwards. This is now equal to 1/4 times a sphere with 2 dots on it. But that was, we said anything with 2 dots on it was equal to 0. And similar arguments, you can quickly generalize this and see that whatever the Euler characteristic was, you get that result. Okay. So every matrix entry in the differential of one of these complexes is either 0 or invertible. And then the very easy observation is that every complex of this form is homotopic to 1 with all differentials 0. So I know I'm sort of, you might feel that I'm belaboring this point. And you sort of, you know that complexes of vector spaces are homotopic to their homology, so what's the big deal? The reason I'm belaboring this point is that the proof of this statement in this context is sort of the essential step of all of the computer programs that compute khovanov-homology fast. And so it's worth understanding the particular way in which I'm going to prove this if you ever want to know how the programs work. Okay, so let me just show you this. Say I have some complex of the following form. Where, oh, sorry, these are direct sums. Yeah. Where some matrix entry of some differential is invertible. All right, phi for invertible. Let me label some of these other maps. Any complex of this form where there's something invertible is homotopic to the following slightly smaller complex. And here we just put beta minus. What can we do? We can follow lambda, then C inverse, then mu. So that must be it. Okay. It's actually kind of fun to think if you have a complex that's describing handles glued on in cellular homology for a space, what this homotopy is doing and what that term is. That's another exercise. Okay, so there we go. We just iteratively apply this. Anytime we see some matrix entry of a differential which isn't 0, well then it's invertible, and so we chuck it away and remove contractible summands. Yeah. Oh. Oh, sorry, yeah, 0. Yeah, sorry. Yeah, the point is anytime you see a matrix entry that isn't 0, you throw it out using this little trick. And this trick is really just a matter of sort of diagonalizing something here so that this E mapping to F by C is actually a summand that you can homotop away. So the proof of this is easy. It really is just seeing that you can write this as a summand and then seeing that it's contractible. Okay. So I think the right thing. Okay. So I'll show you an example of this in action. But what's the point? Well, now we know, of course, that we didn't lose any information in this first version of the functor where we turned things into vector spaces and then took homology. Because in this version, we take our complex, we find a homotopy representative of it with no differentials. Then we can apply that functor that turns it into vector spaces. But there were no differentials, so the homology step is trivial. We lost no information in taking homology. Okay, so now let me show you an example to see how in practice you efficiently compute khovanov-homology using that. Hopefully my attempt to use technology will work. Oops. No. I have to stand here. Oh, okay. So here's just a little example of how to efficiently calculate the khovanov-homology of the trefoil knot by working locally. So we started with in the first line with just the definition of the invariant of a single crossing in this setup. And then on the second line, we stick two crossings together. And the rule for producing this complex here is to just take the tensor product of two copies of this complex, combining the objects and differentials by stacking the corresponding bits on top of each other. You should have a think about that if you need to have a think about that. In the next step, we look at this object in the complex right here and see that it has a circle in it and use this isomorphism that a circle is a direct sum of copies of the empty object to write the complex like this. A fantastic exercise is to look at these four differentials in here and work out how we got them. All that they are the compositions of these differentials here with components of the isomorphism that remove the circle. Okay, you can work those out. And now we notice there's something that's invertible here. Notice that we're working here in a much broader context than the one I was talking about just a moment ago. We could apply this lemma just a moment ago because, well, we could apply this homotopy because any matrix entry of the differential which wasn't 0 was invertible right away. Okay? Here that's not true, of course. This arrow here, sorry, this is notation that I should have explained. This is just meant to mean two vertical sheets over those two arcs, and one of those sheets has a dot on it. That's the two lines with a dot. It means that take the identity cobordism but put a dot on one sheet. That's some cobordism in this category. It's neither 0 nor invertible. So we can't apply the lemma on that arrow. But we look around and we see that we can apply the lemma on that arrow. That's the identity morphism. So we cancel that off, and we end up with this complex. So this differential here, we take this differential here and subtract from it the composition going around, the three morphisms the other way. We get to here. Okay. So that's a simpler homotopy representative of the invariant for this little tangle. And then we close off the tangle on the right by connecting up the two rightmost points with a strand. Maybe I should have done it. Does this work? Yeah, that works. Okay. So now some nice things happen. Looking, let's explain why this differential here is suddenly 0. Well, before the differential was the difference of two different cobordisms with dots in different places. But when we connect up these strands on the right here, those two dots are now in the same place. They're both just on that vertical sheet. And so the difference cancels and we get 0. Okay, so we have this little complex. We take this circle and expand that using the isomorphism. Notice that there's an identity entry in the differential here. Cancel that off using the lemma from over here again and end up here. And then finally we can close off the tangle a little bit more and get the invariant of the Hopf-link, which is just this complex with no differentials. It's already in that form that we knew this lemma would let us get to. I guess I hadn't said this before, but the people often talk about the two-variable Khovanov polynomial of a link, and that's just the polynomial that records where these summands are, their q degrees and their homological heights. So there's a t to the 0 times 1 plus q squared, which keeps track of these two guys in homological height 0, and a t squared times q to the 4 plus q to the 6, which keeps track of these two guys in homological height 2. Okay, so there are three little exercises that you could enjoy doing. Verify at t equals 1, that polynomial is the Jones polynomial. Go back and understand all the steps in this calculation. It's in the lecture notes from yesterday. And then go one step further and compute the khovanov-homology of the trefoil. And of course, you should start with this step, with this simplified complex for the two crossings, and add another complex, add another crossing to that and simplify again. Okay, that ends that example. Well, and it also ends half an hour into this talk what I'd sort of had in mind to do all yesterday, and I'll finally start talking about the things we had planned to talk about today. Before that, let me just say one more thing about this setup and the argument that we had here about complexes having homotopy representatives without differentials. We worked over C, or we worked over a field. It's interesting, and lots of people are interested in doing khovanov-homology over the integers or over something else. And then you see torsion with respect to the ring you're working over. And these lemmas all just fail, and you have to take homology. You have to apply this functor maps from the empty diagram and then take homology in order to get a useful invariant. You see torsion, and it's unclear whether the homotopy type of the complex records any more information than you see in the homology there. I don't like integer torsion, so I won't say anything more than that. Okay, so the two other things that need to be covered when talking about khovanov-homology are functoriality and deformations of khovanov-homology. They're actually they're pretty closely related topics. So if you remember going right back to the beginning of yesterday, I'd said, if anyone is following along in the lecture notes, I'm now finally in the new page that I had at the back of the hall today. If you remember right back at the end of yesterday, I'd said that khovanov-homology is a categorical not invariant. We associate objects in some category to links, and to an isotopy of links, we associate an isomorphism in that category. I haven't told you that isomorphism yet, and we better do that now. So what do we do? So to each Reidemeister move, we write down a particular homotopy equivalence. I certainly won't do this today, but you can look it up in various papers. So for example, if we look at KH of this little tangle, so in the language that I've been using so far, the khovanov invariant of this tangle is some element of this Hom space from 3 points to 3 points. And we have to pick a particular homotopy equivalence between that complex there and the complex that we get from looking at this tangle. And similarly for the other Reidemeister moves. And in particular, we have to do this for all different orientations of the Reidemeister moves. Okay, and we can do more. We associate chain maps to Morse moves. These are chain maps that aren't invertible, they're not equivalences. But these are actually extremely easy to define and understand. Here it's complicated, you've got to go and write particular things down. But here it's sort of obvious. Let me just say what I mean by Morse moves. Well, these are cobordisms of links where you create an unknot, where you kill an unknot, or you do a saddle cobordism somewhere inside your link. And I'll use this example to just show you what these chain maps are. They're nice and simple. I should have written this board somewhere else because I want to line things up with this. Okay, let me be evil and erase this right after I've written it. So say that we want to look at the cobordism from this link to another link, say the saddle move in between the two crossings. Okay, well, the complex for this is pretty easy. Maybe I'll leave out the factors of Q to save myself a little bit of time. sloppy board work. Okay. That's just following the rule again. And there's an obvious chain map from this complex to this complex. It's just the diagonal chain map. We map that object to this object by doing this same Morse move in the same place. We map each of these objects to each of these objects by doing the same Morse move in the same place, and so on. Okay? The chain maps associated to Morse moves on complexes are always just diagonal. They map each object, each resolution to the corresponding resolution. Okay. Now, we can take an arbitrary isotopy and write it as a composition of elementary moves, which are just Rademeister moves and these Morse moves. The problem is that there's no unique way to write an isotopy as a composition of Rademeister moves and Morse moves. And so if we just try and define the chain map we want by taking the composition of all the chain maps, we have to be careful. You can't write an isotopy uniquely as a composition of Rademeister and Morse moves. So fortunately, there's a way out of this. Let me just show you an example of the sort of thing that can go wrong. Here's a little tangle. We could do the following sequence of moves. Here's a Rademeister 2 move. There's a Rademeister 3 move. There's another Rademeister 3 move. And there's a Rademeister 2 move done in reverse. It's easy to see that the surface you get traced out by doing these moves is just isotopic to the identity surface. Maybe at the end I should, really to get back to where I started, I could just move that strand back down again. The surface traced out by all of this is isotopic to the identity surface. So we better hope that if we accidentally wrote down the identity as this composition, that we get the same chain map, we get the identity chain map. But it's all fixed for us. We just meant to compose all of those Rademeister moves in turn. Okay. The problem is, however you pick the chain maps for Rademeister moves, this composition is minus the identity. That is the chain map minus the identity. Okay, so I think all I'm going to say is that there's a fix. It involves something called disorientations, and I won't say anything more about it. Just pretend for the rest of what I have to say that there isn't this problem, and that we get well-defined chain maps from isotopies by chopping up the isotopies as compositions of Rademeister moves and composing the chosen chain maps. Okay. This thing, use disorientations, is just going back and tweaking this category C star I described. You have to decorate the surface as you look at it a little bit and add a few more relations that deal with those decorations, and then the sign problems go away. This has something to do with categorifying SU2 instead, well, the SU2 quantum invariant of knots instead of categorifying the Kaufman bracket invariant of knots. Okay. I guess I won't write anything more than that. Okay, so let's pretend now that khovanov-homology, as I defined it, is an honestly functorial thing. We know that there are these sign problems, but we can make them go away. So then the final thing I want to talk about is deformations of khovanov-homology and how we get the S-invariant, and a lower bound for the sliced genus of knots out of khovanov-homology. So I want you to remember a long time ago when we were talking about all of these identities on surfaces, one thing in particular we'd said was that anytime we had two dots on a surface, we set that equal to 0. Let's go and relax that condition now and see what we get. Now, there are a few different ways you can go about relaxing this condition. Oh, sorry. One way, the old-fashioned way, well, sorry. The first way to do this was to instead have that anytime you see two dots, this was alpha times a sheet without dots for some non-zero complex number. Okay? But that's a bit drastic, and for one, it fits sort of badly with the description I gave yesterday, where remember we wanted some Euler characteristic condition on surfaces that would break here. That Euler characteristic condition counted the number of dots on surfaces, and so these pictures wouldn't even be in the same home space anymore. So let's do something slightly different. Let's work over C adjoin alpha instead of C. And now, let's not say that alpha is invertible. It's just a parameter out in the coefficient ring. This will have a nice advantage. I'm going to show you how to explicitly compute the S-invariant of a knot without having to play with spectral sequences or anything like that. But notice that something goes badly wrong. It had been really important a moment ago that we're working over a field, and we're not working over a field anymore. So we have to be a little bit careful there. Okay. So before, well, okay, so the question, I meant to repeat questions. The question was, is there a reason why you don't just want to take rational functions in alpha? Let me answer that by saying something that I omitted a moment ago that will make it clearer why we don't want to do something like that. I'd complained that if you set alpha to be just some non-zero rational number, that this relation would break the homogeneity of the relations. These guys would have different Euler characteristic counts. So to fix that, when we work over C of alpha, we have to give alpha a formal Euler characteristic of -4. So that just means if you see some multiple of a surface, and that multiple includes alphas, you count the surface as if it had lower Euler characteristic than it really does. Now remember that we're only ever interested in linear combinations of surfaces that are homogeneous with respect to Euler characteristic minus twice the number of dots, well, and with this fix as well. And what that means is that the only way that we ever see alpha is just as powers of alpha, constant powers of alpha multiplying surfaces with the same Euler characteristic. So when I say working over C of alpha, you never actually see a polynomial, you only ever see monomials. And given that that's all we ever see, it would maybe be strange to do anything else. I know that's not a good answer. You'll see how alpha shows up in examples. Maybe not actually. Okay, so before every complex in this home space where all our link invariants live decomposed, yeah, I want to say decomposed as a direct sum of of copies of q to the s times the empty diagram. So here, in any homological height. So here I'm making the strong statement that every complex has a representative with no differentials. That is, it's just think of this guy in some homological height as a complex all by itself, concentrated in one height with no differentials. And every complex is just a sum of those. That, of course, stops being true. But we get something almost as good and kind of interesting. What we get is that every complex in the Hom space from one point to one point decomposes as a direct sum of complexes. So we'll give these guys names. E, that's just a single step complex. The object is just a single strand that's in this Hom space. No differentials, but you can put this in any Q grading. You can multiply it by Q to the S for any S, and you can put it in any homological height. And the other complexes you get are C sub n, which look like this. So this is a two-step complex. The objects are both, well, it's a strand and Q to the 2n times a strand, and the differential is just n dots on a sheet, okay? Back when 2 dots were 0, C2 would have just been 2 copies of E in different homological heights, but now it's some indecomposable complex. Okay. I'm not actually going to prove this, but the proof is simple, especially if you love algebra, and you can do it very explicitly by looking at that lemma that I had before, that homotopy equivalence that stripped off a direct sum end, and just think about what you can do if, instead of seeing an isomorphism somewhere, you're working over C adjoin alpha, and you see alpha to the k times an isomorphism somewhere, and higher powers of alpha multiplying everything else. And if you think through applying that lemma in that situation, you get this result here. Okay. So let's just have an example, which is also an excellent exercise, which is that if we take the khovanov-homology of the cut-open trefoil, so because this theorem only applies to complexes in the 1 goes to 1 space, we're now going to think about invariants of knots by cutting them open at a point, turning them into 1-1 tangles and sticking them into this Hom space. The khovanov-homology here just looks like Q squared times a strand. Then there's no object in this and that's in homological height 0. No object here. Then Q to the 6 times a strand here. A sheet with a dot on it. And Q to the 8 times a strand here. If you've already done the exercise that I suggested before of computing the khovanov-homology of the trefoil, you would have got to this answer as an intermediate step in that calculation. And let's just write this a little bit more succinctly. This is Q squared times E, direct sum Q to the 6 times T squared C1. So that's just saying a copy of E, but shifted up by Q squared, and it's sitting in homological height 0. That was the underline, so there's no factor of T here. And then there's a copy of C1, but it's shifted up in homological height by 2, hence the T squared, and there's an overall factor of Q to the 6. Okay. Something worth pointing out is that the coefficients that appear here, sort of the coefficient, a polynomial in Q and T that appears in front of E, and the coefficients that appear in front of each Cn, are each individually invariants of the knot. If you know and love the spectral sequence description of Lie homology and khovanov homology, these invariants, the coefficients in front of each of the C to the n's, are capturing all of the information in that spectral sequence. Okay. what do I want to say about that? Well, the first thing is a theorem of Lee's, which in this language says that if you have a link with k components, there are 2 to the k minus 1 copies of E. There's actually a very nice diagrammatic proof of this theorem, but I guess I won't do it today. So you can check for the trefoil, we had 1 copy of E, and if you went back to the calculation that I guess that I showed on the overhead, there were 2 copies of E in the invariant of the Hopf link, and in fact, that was all in the Hopf link. It was just 2 copies of E. Okay, so then here's a definition. The S-invariant of a knot is the power of Q appearing with the unique copy of E. And said this way, this is a great definition because we've seen that the S-invariant is explicitly computable. You take your complex for the cut-open knot, and you just apply that homotopy lemma, the stripping off a summand over and over again, and you know that you have to get into this form, and you'll see the power of Q that appears in front of the 1 copy of E. If you don't think of the S-invariant in this way, then the definition of the S-invariant is a little bit complicated. You know that you have this crazy spectral sequence, and you know that not much survives on the final page, and you have to look at the pre-image of the things on the final page and find the maximum height that any pre-image sits in. And I think this is a more computable way to get at the S-invariant. And there are programs. Part of the knot theory package has a program that uses exactly this method to give you the S-invariant of a knot. Okay. So then the theorem. Okay. The theorem of Rasmussen is just that the absolute value of the S-invariant divided by 2 gives a lower bound for the slice genus of the knot. So this is just look at all surfaces in B4 meeting your knot in the boundary S3 and just take the minimum genus over those surfaces. Okay, now I guess in the 5 minutes remaining I can actually just prove this theorem because in this setup, well, okay, prove it with one gap. But it's conceptually very, very easy in this setup. Let's just look in the example of the trefoil and we'll see what's going on. Actually, well, no, let's not look at the example of the trefoil. Let's just take any knot. So here we've got kh of a knot. So in this last part of the talk, I'm only talking about knots, not links, because I need there to be a unique copy of E. And I see that it's got q to the s times E, direct sum, a whole lot of other stuff, all of the CNs. And I think about a surface. Well, sorry, I should write k cut here, okay? So now let's think about some surface which bounds the knot sitting in the foreball. And let's first of all delete a disk from somewhere inside. So it's now a cobordism from the unknot to our particular knot. And now let's cut open the whole cobordism by picking some interval on the surface, joining the top knot and the bottom knot, and slice it open. So that then is some cobordism from a single strand up to the cut open knot. Okay? So between these khovanov-homologies, we get, via functoriality, a chain map determined by the surface that we're looking at. Well, what's down here, it's easy to check that the invariant of a single strand is just q to the 0 times e. The S invariant is 0 here. So the step that I'm not going to prove standing at the board, but is again admits a really easy diagrammatic proof. Well, actually, sorry, not quite as easy. This theorem of Lee's has a very easy diagrammatic proof. This lemma here, if you want to see the proof, then you actually do have to look at the definition of the chain maps that we use for the Reidemeister moves, and you need to check something about each of those chain maps. Okay, so the lemma is just that a connected cobordism from the strand to a cut-open knot is non-zero between the two copies of E. Okay? And this is, I mean, once you go look at those chain maps, this is just saying, well, sort of, well, yeah, I guess I won't try and explain that. Okay. So what's that? Well, we've got some non-zero map here. What can that map be? Well, we know what the homs are from a single strand to a single strand. They're all just some sheet with some number of dots on it. Okay? But we also know that there's this grading condition, this Euler characteristic condition on homs. And so maybe I should just try and recall that. To be in a hom from q to the kd to q to the k prime d prime, the condition is that you need to have the Euler characteristic equals k minus k prime plus twice the number of dots plus half n plus m, where here d and d prime are both diagrams with endpoints at the bottom and endpoints at the top. So let's just look at that formula here. Well, the Euler characteristic of this surface is just 1. It's a disk. K is 0, because we're starting at q to the 0 here. K prime is S plus 2n plus 1. Okay? Sorry. Sorry. That 1 there was me being very hasty. That Euler characteristic there is the Euler characteristic of the surface, of the cobordism that we're looking at, from the strand to the cut-open knot. So I better leave the Euler characteristic there. Okay. Now let's just rearrange a little bit and write this. Well, okay. Let's just observe that the number of dots must be positive. Okay? We don't have negative numbers of dots. So this quantity is positive, and so we can write that, rearranging a little, that the Euler characteristic minus 1 is greater than negative s, or the Euler characteristic over 2 is greater than negative s. Okay? This number here, if you think about what we've done to our surface in the four-ball, this number here is exactly the genus of that surface. Okay? And we've seen that the genus is at least negative the S invariant. Sorry. I got my factors of 2 wrong somewhere. I didn't divide by 2 over here. Very good. Okay. It's at least negative S over 2. Now, why the minus sign in the theorem but the negative sign here? We can just look at the mirror image of everything. When you take the mirror image of everything, all of the powers of Q get negated, and you get the same inequality the other way around. That gives us the theorem. Okay. I think I've got either 1 minute or less than 1 minute, either plus 1 minute or minus 1 minute. So let me just say one thing about this, this theorem over here, that every complex admits a decomposition like that. Well, that gives you a bunch of nice invariants that tell you all about the spectral sequence for khovanov-homology. And a conjecture, and the only reason I'm going slightly over time to write this up is that Peter Horn told me something out in the hall just this morning that seems to indicate that maybe this conjecture is false. And so I'm very excited to hear the details. The conjecture is that you don't see high CNs, you only see C1 and C2. And the neat little corollary of this conjecture is that the S-invariant of a knot you can just read off right from the two-variable polynomial. Remember that this is a polynomial in Q and T, so just leave Q there. Well, maybe I'll write Q to the SK on the left-hand side. And I substitute in T equals negative Q to the negative 4, and I divide the whole thing by Q plus Q inverse. If this conjecture is true, then this is a really easy corollary, that you can read off the S-invariant from the two-variable polynomial. Now, of course, perhaps the conjecture is false. Maybe Peter's seen evidence that it is false, and I don't think anyone has any idea how you might prove it. It turns out that knowing this decomposition, you can think about what it means for the two-variable polynomial, and you can discover that the two-variable polynomial constrains the possible decompositions into E's and Cn's. And even though there might be multiple different decompositions which are compatible with the two-variable polynomial, in practice, often, they all share the same value of S, that is where the copy of E sits. And so in a great many cases, you can read the S-invariant directly from the two-variable polynomial, but perhaps not always. Yeah, I'll finish there. Thank you.